we talked about divergent plate boundaries. Now we have convergent plate boundaries. Divergent is where plates are moving apart. Convergent is where plates are moving together. And they're classified based on what type of crust is colliding on the plates that are interacting. There are three subtypes of convergent plate boundaries: ocean continent, which you can see in A, ocean, which you see in B, and C, which is continent. And they have different features in each one. There are some features that are similar to both, and I guess we could talk about the things that are same on this slide. So continent is destroyed at all of these. There is a plate going underneath another one. Here we have at ocean continent, the lithosphere of both is interacting. The continental crust kind of stays along the top, but the lithosphere of the oceanic crustal plate ducks down below where there's some melting of the lithosphere there. Same thing occurs when you have ocean. The colder, older, denser one goes underneath, and you have more destruction of the lithosphere. Even when you have continental collision where we get mountains and stuff, some of the lithosphere of one of the plates is being pushed downward, even if the continental crust on top of both is being pushed upwards. One of the features that's unique to two of them is this volcanic arc. Basically, the way a volcanic arc occurs is when you have that melting of crust, because it's made out of lighter materials, organic materials, sediments, and stuff like that, that as it melts, it begins to rise up through the crust of the other plate. And you end up with a chain of volcanoes that can occur sort of along both. And that's called a volcanic arc. And it can occur with either ocean continent or ocean plate boundaries. Let's talk a little bit more about the ocean continent. There's a lot of information on this slide, so I'll try to talk, or maybe I guess you'll pause. The general idea is that oceanic crust is more dense than continental crust. And if you look at these numbers, it looks like it's not that much more dense, but it's enough to make plate tectonics function the way it is. Granite, which is continental crust, is 2.7 grams per cubic centimeter, while basalt, which underlies all plates, is 3.0 grams per cubic centimeter. And when they collide, an ocean and a continent, the oceanic plate will dive down because it's more dense, and the continental crust will rise over the top. When you get a volcanic arc from these, you get a mixture of the granite and the basalt being sucked downwards through friction, and you end up with that mixture is called andesite. Andesite volcanoes tend to have very strong volcanic eruptions compared to just plain old basaltic volcanoes, because they have a lot of different materials in it and you get a lot more gas. Mount St. Helens is a classic example of a andesitic volcano eruption. You have the Cascade Mountains, which you can see right here, are actually a chain of andesitic volcanoes created by the Juan de Fuca plate colliding with the North American plate. And you get andesitic volcanoes because there's subduction going on right along here. The arc that you get is called a continental arc or continental volcano arc, and it's kind of a unique one. There's a few other examples. Now, when you have ocean-continent collision occurring, you get a trench, and the trench is only really obvious and really well developed if the area of spreading is very far away from the place where the trench develops. And an example of this is the Peru-Chile Trench along South America, where the spreading center is so far away from the trench. But the Juan de Fuca is kind of unique because we have the spreading center right here and then the trench right here. On global scales, they're right next to each other. The Juan de Fuca is actually an area that's of great concern right now in terms of geology, and it's getting a lot of study. The Neptune Ocean Observatory, which we'll talk about later, is on the Juan de Fuca because people are so concerned about it, especially for its potential to generate tsunamis on American coastlines. Additionally, we have convergent ocean. The plate that goes underneath the other one will be older. The reason why it's older is because as you move away from the mid-ocean ridge, the basalt becomes more dense because it's colder. So the farther away you are, the older you are. So the older plate will be subducted. The deepest oceans in the deepest trenches in the world are found at ocean plate boundaries, such as the Marianas Trench, which can be almost 11 kilometers deep. And you get island arcs along these, and along the Pacific, there's many island arcs due to the interaction of the Pacific plate with some of the smaller plates. And these are the ones that are associated with trenches. We call those volcanic island arcs as opposed to continental island arcs. And they're based on basaltic volcanic activity. And these are all examples of them. I want to say balsamic like vinegar. Basaltic volcanic activity is more constant but less eruptive. There are, of course, exceptions to this, like Krakatoa, but the Ring of Fire, as we call the plate boundary of the Pacific Ocean, has almost constant volcanic activity, but generally it's not as strong as the rare activity that is associated with continent ocean plate boundaries. Hold on. The last specific type of convergent boundary we'll talk about is continent-continent. There's only one really good example of this, so there are a couple of other non-classical examples. Basically, the India plate, which is part of the Indo-Asian Australian plate, is an area of continental crust colliding with continental crust, and you get an area where you have mountains formed. The Himalayan mountains are the biggest mountains because the India plate is still colliding with Asia, and it will for 45 million years. What's interesting is India used to be all seafloor, and you will actually find fossils of seafloor animals at the top of the mountain, the Himalaya mountains, because of that. Please note that there is still subduction occurring underneath the Himalayas. It's just a very small amount. All of the continental crust goes upward, and a small amount of the basaltic crust goes below. The convergent plate boundaries, earthquakes that are associated with them, tend to be shallow. Divergent plate boundaries. Their earthquakes we talked about are weaker, and they're more shallow. Trench earthquakes, as the process of pulling crust in and destroying it is very tectonically powerful. They have deeper earthquakes because the trenches themselves. A trench, while it may sound superficially very similar to a mid-ocean ridge, they're very different. Trenches are much deeper, and they have some of the deepest earthquakes and most powerful earthquakes. Remember, the crust is actually being bent downward, and this is rock. So when it bends, it can frequently begin to shatter, and that shattering is what we call an earthquake. The seismic moment scale put the Chilean earthquake at 9.5. The one in Fukushima was close to that. There's also a trench right there. So these convergent plate boundaries that they have much stronger earthquakes. We'll talk about transform plate boundaries in the next video.